how memory management works in modern systems. So, mm, why do we actually require management of memory? Because when it comes to any device, whether it may be phone or laptop or an iPad, we are not going to run a single program at a time. There are going to be multiple programs at the system level as well as the programs at the user level, which are running at a time simultaneously most of the times. So the concept of memory management is really important when it comes to the systems. So before we get into what points the first slide is saying, we first need to know what a program is. A program is a set of instructions which can be for any sort of function, like for suppose starting up an app, etc. So every program believes it has total exclusive control over the system's memory. The reason why it is represented in such a way is that each and every program which is running within the memory is isolated. Means that they don't have any connection with the other programs which are running within the memory. So every program seems to be running having control over the system's memory. So that's the reason why it is represented in that way. And when it comes to the processes which are happening within the system, these work in microseconds. These orchestration of these work between the hardware and the software happens in microseconds. Our goal, we need to understand the mechanics behind the illusion of infinite, isolated, and instant memory. Okay, so you'll get to understand this particular uh, figure as we go on with the next slides. Okay, orchestrating the chaos. There are four main concepts for this, which is isolation, efficiency, speed, and safety. Isolation means that each and every process is going to get a private workspace. It means that each and every process is isolated such that one process cannot have any connection with the other process which is running so that they don't interfere with each other. And the other point is efficiency. The physical RAM is utilized optimally with inactive data moved out because the RAM which we have within the system is limited, right? Based, of course, it is dependent on the specs of the system. It can be 4 GB or 8 GB or 16 GB or 32 GB, but it is limited, right? So it is utilized optimally, such that if there is any program, if there is any data which is not required, which is inactive, which is not being utilized, then it will be moved out so that the data corresponding to the process, which needs to be running actively, will be sent in within the RAM. Speed. Data access remains fast despite complex translations behind the scenes. The reason for it is because the data which we have within the system is divided into multiple layers. It is all dependent on how close it is to the central processing unit, the CPU. Within the CPU, we have the registers, and afterwards, we are going to have the cache memory, and we are going to have the RAM, and we are going to have the disk memory. So, depending on how close it is to the CPU, the speed is a variable. Like the closest it is, the fastest it is. So the registers is the fastest memory type within the systems. Safety, strict permissions ensure read-only code and secure execution boundaries. So for all of this data to be safe, there are mainly three different types of permissions, which are read-only permission, write-only, and execute permission. Let's go for the next slide. The architectural cross section of a process. This cross section is of the memory within the process, like how it actually works. So mainly we are going to have the stack, the heap, basis, data, and text. The stack is the memory unit where the function calls, local variables which are active, uh, take up the space. The heap is a dynamic allocation memory where long-term data structures regarding the particular program will be held. BSS is the memory type where the initialized variables stay. The reason for it is because the memory, the stack and the heap memory are limited, right? So if the variables are not initialized, they are not used by the program. So they're just going to take up the space unnecessarily. So they will be taken up by the BSS. Data, these are the initialized global variables, global or static variables. The text, compiled machine code. This text will be the corresponding text of the what we are actually have in the higher level language, which is the human readable language. So let's take a look at the text which is given in here. The stack goes down, the heap goes up. The reason for it is because the stack you can understand it based on a stack of books. So they are going to put in and it goes up by the layer, right? And when it comes to the heap, it goes up. In the stack, it goes down. Like the process, I mean, suppose if we consider the stack, the process, the program which is at the highest level will be executed first. It's like last in, first out, LIFO. This is entirely a virtual layout. It does not look like this in physical RAM. So these are representation which we actually take for the virtual. You'll get to understand this as we go on. So what it actually means is that this is not how it actually looks in the physical RAM. The way it is represented within the physical RAM is completely different. Developer view, stack versus heap. Let's get to know the difference between the stack and the heap. The stack, the speed is it's extremely fast. Okay, the reason for it is because it is going to consist of the function calls, right? Function calls in the sense, mm, let us consider you are you have a I mean, let's consider the example of a website, okay, and you are trying to click, and for that button to be clicked, the function needs to be called, right? So it can be represented in that way. So like these function calls, like for the function of that particular aspect to run, this function is to be called. So all the function calls are within the stack. So it needs to be extremely fast. The heap is slower. As I have mentioned in before, the long-term data structures, like the these type of data would be within the heap. Management. The stack is automatically managed. It is managed by the CPU or the compiler. When it comes to the heap, it is managed manually. Like we are going to manage it. Like for suppose there is a programming language, and we can manage it manually by using malloc, which is a type of method which we have in C or C++ language, or garbage collection by Java or Python. Limits. The stack is limited size. The heap, it's flexible, limited only by the total system memory. Typical use case, the stack, it's a short-term workspace, and when it comes to the heap, it's flexible and long-term data structures, which is used for long-term data structures. The virtual reality of memory. Modern programs never touch physical RAM directly. Yeah, this is true. You'll get to know how it works as we go on. Every process operates in its own private, contiguous virtual address space. As we have talked before, this is the concept of isolation. The OS creates this illusion to simplify development and isolate process. Okay, this illusion is created for the process so that the development will be simplified and the processes are isolated. Behind the scenes, memory is fragmented and shared across the physical hardware. As you can see in this image, you can see that uh, it's not allocated in a strict way, like suppose this and put that in. So how it is actually assigned is based on there are two different types of addresses. One is uh, physical address and virtual address. So these both addresses will be connected, and that's how we are going to utilize that particular space which we are using, which will be represented by the virtual address space. The translating switchboard, the MMU. MMU is a memory management unit. It's a hardware chip that translates addresses. Like we need to translate, as we have talked before, we have two different types of addresses, right? The physical address and the virtual address. So these both needs to be translated so that the there can be a connection between these both. Paging, virtual memory. So as I have talked, there as we have two different types of addresses, there are two different types of memories, right? One is the physical memory and another is the virtual memory. Virtual memory, the individual components within virtual memory are called as pages, and the individual components, the fundamental components with units of physical memory is the frames, the page table, the OS master ledger mapping virtual pages to physical frames. So these virtual pages will be mapped to the physical frames. The program asks for a virtual address. The MMU intercepts and reroutes it to the physical hardware. So what it actually means is that the program is never going to have access to the physical RAM. There is this intermediate component, which is the memory management unit, where exists the virtual space, which is linked to the physical RAM. So what it actually means is that the software is going to have access only to the virtual address. It can never have access to the physical frames, physical addresses. We have this intermediary, which is the memory management unit. As you can see in this, the software request load from virtual page 4, and this page 4 is connected to the frame 12. So this address will be translated by the memory management unit, the virtual address to the physical address, and the data which is required will be fetched. Demand paging, and the page fault. Demand paging. Memory is loaded from disk only when explicitly needed. So it means that only the data which is requested will be loaded into the RAM from the disk. By the way, RAM full form is random access memory, if anyone doesn't know. And the disk space is called as a read-only memory. A page fault is not an error. It is expected hardware interrupt. Okay. The reason why we actually require is that, suppose the RAM is full, and mm, if you require, we need more space for the program to run, right? So what actually happens is that there is going to be a swapping which occurs where the NAC2 data will be sent off from the memory, and it is going to fetch the memory which is required by the process into the RAM. So this is an interrupt which happens so that the process is stopped and the necessary data will be fetched by the OS. Execution seamlessly resumes only once the page table is updated. Okay, as you can see in here, CPU requests memory, MMU checks page table, page fault is triggered, CPU pauses the process, OS takes over, fetches the required page from the slow disk drive, OS updates the page table and tells the CPU to resume execution. So it is a page fault is an interrupt which is made so that the required data by the process will be fetched by the operating system and it is resumed once the page table is updated. As I have talked before, this page table in the sense we are going to have a page table within the virtual memory address where the pages are linked to the physical things. When the warehouse overflows, swapping. When RAM is full, the OS evicts in the sense it is going to remove the inactive pages, inactive data to disk swap space. Disk I/O is exponentially slower than RAM access. As I have talked before, the further from from the CPU, the slower it is, and disk space is considered as 1,000 plus times slower than RAM. The risk of thrashing. If a system needs more memory than RAM can hold, the OS spends all of its time switching, swapping. Swapping in the sense the inactive data will be sent off to the system, not system, and the data which is required will be fetched by the operating system into the RAM. And this process takes a lot of time because the disk I/O operations are very slow. So thrashing can occur because of this. So there's always a need for the RAM to be properly utilized. The CPU utilization drops and the system grinds to a halt. The Tetrix matrix, allocation and fragmentation. Continu- Contiguous allocation. Assign memory in solid blocks, leading to massive external fragmentation. So there are two different types of fragmentation, which are the internal fragmentation and external fragmentation. Internal fragmentation means that so we have these blocks of memories, right? If we of these blocks is going to have fixed size. For suppose, let's take a block which is a 4 KB page, 4 KB, and the data which is used within it is only 1 KB. This is called as internal fragmentation because it occurs within the blocks. For suppose if it happens to the whole memory space, like it is the memory is randomly used, then we wouldn't be able to find a space particularly within the memory within the memory space, and it needs will get fragmented, right? So this is called as external fragmentation because contiguous allocation is required. Like there needs to be a continuous allocation. We cannot divide it. Suppose a new request happens, and this request cannot be divided to divided as you can see within the space. Like there are 8 blocks, and this requires around 10 blocks, and we wouldn't be able to divide it into 8 blocks and 2 blocks and put it in there. So this allocation will fail because of it, because we require continuous allocation, which is the olden way. This is called as external fragmentation. Isolation and memory protection. Virtual memory inherently isolates processes. Process A cannot physically address process B's memory. As we have talked before, this is the concept of isolation which we have in memory management. The OS enforces kernel mode versus user mode separation. This is because the internal processes which are running the core unit within the operating system is the kernel, and the user mode is just we just going to require the higher level abstraction, right? Page permissions. Every page carries read, write, and execute blocks. So these are the three main permissions which can be held for the process. Attempting to write to a read-only page triggers a fatal OS exception. These exception lessons it's an handling which occurs when in these type of scenarios where the permission which is given is only read only, and if you request for to and if you try to write, and that wouldn't be possible, and it can cause an OS exception. The cleanup crew, garbage collection. Garbage collection is a concept which is there in programming languages like Java, Python. C and C++, what is actually different when it comes to C, C++, and Java, Python is that garbage collection is automatic. It's a concept which is automated, but when it comes to C or C++, as we have talked before, they use malloc, which is manual memory filling. But when it comes to Java and Python, which has a garbage collection, it is automatic. Reference counting. The runtime tracks how many pointers target an object. At zero, it is deleted. It means that, for suppose that particular item is not required, then and it doesn't have any pointers to it, it will be deleted because it is in active stage. Mark and speed. Like for suppose if there is an uninitialized uninitialized variable, it will be deleted because it is not used after. Mark and sweep. Periodically traverses all active references. Any unbraced memory is reactive. Okay, as you can see in this, these if there is any unbraced memory, then it will be reclaimed so that that memory can be used for by other active variables. The memory hierarchy blueprint. As you can see in here, the disk or SDD is a larger. Physical RAM is the next largest. CPU cache, which are the L3, L2, and L1 are the L2, L3, L2, L1, and next is the CPU registers. As you can see in this reverse pyramid, as we go from the top to the bottom, the size decreases. As we go from the top to the bottom, the speed increases. This is the difference because, as I have talked before, central processing unit. The closest you are, the memory is to this unit, the fastest it is. And it is also more expensive. The amount of registers which we have in a CPU is just around some KB. It goes the same way for L3, L2, and L1. Physical RAM is around GBs, and disk space can be in TBs, terabytes. The OS and hardware collaborate to keep the most within data as close to the CPU as possible. So, for suppose if there are any CPU instructions, the core CPU instructions will be within the registers. And when it comes to the cache memory, like the most frequently used data will be within these limited memory. That's how it works. Registers instantaneously but extremely scarce. CPU cache nanosecond access stores recently used RAM data. The frequently used data will be stored within the cache. Registers mostly have CPU instructions, the system processes. RAM and disk high capacity but exponentially slower to access. Yeah, if we consider the difference of speed between cache and RAM, it's exponential. It's in the same way for RAM and disk. The fastest is the register and the slowest is the disk. Advanced scaling operations. Optimizing system performance through specialized memory and process management techniques. We have three different types mentioned in here. One is the copy on write. When a process forks, memory is shared until modified, saving massive amounts of RAM. Like for suppose there is a process A and process B, and the process P1 and process P2. We are going to have a shared memory until we are going to have a modification. Like for suppose process P2 is going to trigger a write, Then a new memory will be allocated to it such that there won't be any, there will be proper isolation between P1 and P2 because within a write operation, it can have changes on P2, right? It can make changes on P1, right? So that's the reason when it triggers a write operation, like for suppose a process P2 requires a write operation, then a new memory will be allocated to it. Till then, we are going to have a shared memory. This is called as a copy on that. Memory mapping maps disk files directly into virtual memory for high-speed file access. So, as we have talked in before, the, these are actually stored within the physical memory, right? The data is actually stored in the physical memory, and we are going to fetch it by the memory management unit is going to translate the virtual address to the physical address, and it will be fetched to the physical virtual memory from the physical memory, and it will be accessed by the program. But if we are going to require faster access, then these disk files are directly uh, put in within the virtual memory itself. This will cause the speed to increase a lot more as there is the main step which is communicating with the physical memory. That step will be removed, right? When this happens, so it will be very fast. This is memory mapping. NUMA, non-uniform memory access. Memory access time depends on whether the RAM is local to the requesting CPU. For suppose there is CPU 1 and CPU 2, which are mode 0 and mode 1. Mm, if it is accessing within it itself, like within the local RAM, within that itself, then it will be fast access. But if it's trying to access from the local RAM of node 1, then it will be slow. This is called as locality aware, non-uniform memory access. When a CPU is trying to access the local RAM of another CPU. Synthesis, life of a memory request. The application requires a virtual address from the heap. Okay. The hardware attempts to find it in the ultra-fast CPU cache. RMS, the MMU translates the virtual address to a physical frame. The virtual address will be translated to a physical frame, physical address. The physical RAM is accessed and data is pushed up to the hierarchy to the CPU. All of this occurs in mere nanoseconds, millions of times of a second. App request, which it is going to app is going to have access only to the virtual address. This virtual address will be sent to the L cache, and this cache will be accessed by the memory management unit, where the translation of the virtual address will happen to the physical address. Like, or it can also mean that pages will be will be mapped to the frames, and it will be fresh from the physical memory. And we have the CPU register. This will be loaded to the CPU register, and the central processing unit will be will do the process. So this is what actually happens when within a life of a memory request. Okay, let's go for the last. We have a common pitfalls when it comes to memory management. One is stack overflow. Like as we have talked before, the stack is limited, right? So if you are trying to have recursions in the sense you are trying to call a function again and again, and it's very multiple times which the stack cannot handle. A stack overflow happens where the limit is breached, and we have the memory leaks allocating on the heap, but forget to free it. Like we are going to allocate to the heap till its limit, and we are not, and if it is not freed of the inactive data, then memory leaks happens. So we want to know everything about the memory management. This is it. We can have a look through about the theory. Programs operate in a virtual illusion. Paging and the MMU silently map this illusion to the fragmented physical reality. The ultimate goal is balancing isolation, capacity, and blazing speed.